Hi, everybody. Welcome to this webinar, which is hosted by the IBIPSA Education Committee. I'm Pamela Fennell, and I'm the chair of the Education Committee. And I'm delighted to welcome today Aisha Demir, who's going to be talking about the impact of spatio-temporal resolution on the calibration of urban energy models. So this webinar series is very much part of the IBIPS Education Committee's core purpose. And there are three elements to that part. That is about identifying education and training needs throughout the community. Part of it is about initiating, developing and coordinating new education materials and methods. And then the final part is about offering training sessions. And crucially, those training sessions like this one are open to non-members as well as to members. So the format that we're going to go through today is the same as previous sessions. So if you've been to some of the other webinars in this series, you'll be familiar with it. I'm going to take the opportunity to ask you a few quick questions. I hope that you'll have time to respond to those. Then I'll invite Aisha to give her presentation. During her presentation, you'll be able to put questions into the Q&A button. So that there's a box for Q&A. There's also a chat, but we won't be able to use the questions in the chat. So please just put questions into Q&A. And then at the end of the presentation, I will read those questions out and put them to Aisha. So before we get to that, I would just like to ask you if you would mind telling us a little bit about yourselves. It really helps us to plan these seminars to get a better sense of our audience. So the first question I have for you is, which of the following best describes the role in which you use building performance simulation? So do you consider yourself a professional using it as part of your professional role? Are you a student learning about building performance simulation? Or are you an academic, perhaps teaching or carrying out research on building performance simulation? So you can see the code for the Mentimeter at the top there. And so please do join and let us know what you think. Great. There's a few more answers still coming in there, so do feel free to keep putting those in. I'm going to move on to my next question now, which is, where in the world are you based? It's always a tricky question because there are lots of people who will be based in one country, but perhaps doing research or work in another country, but do just give us a general sense of where you are. Brilliant. Thank you very much for all those responses. That's really helpful. I'm delighted to see that we're getting so many responses from people who are perhaps not even in a time zone that makes this terribly convenient. So thank you very much for making the time to join us. And now, Aisha, I'd like to hand over to you. So I'm going to stop sharing my screen. And if you could share yours, and it would be great to hear more about the impact of spatio-temporal resolution on calibration of urban building energy models.
Are you guys able to see it?
Yes, we
awesome.
can. Could you just put it on slideshow mode? I think that's all we need.
I think it's in the slideshow. It should be.
So we can see your yeah.
Notes too?
We see the notes as well here.
Oh, okay. Let me see. It might be because of the I have two screens. Let's see.
Perfect.
Okay, cool. This is Aisha, Dr. Aisha Demir, and I am an assistant professor at University of Wyoming. It's early in the US, not too bad though. So today I'll talk about the impact of spatio-temporal resolution on calibration of urban energy models. And I'll be giving background why we got into this discussion during my PhD, which I defended my thesis in 2022. So it's not completely new, but our publication is new. So and this is like, I expect many of you already are aware of this problem, or this, like, how much buildings are responsible for CO2 emissions and energy consumption. That was the initial motivation behind why I got into, and many of us probably got into research doing in built environment. And we know that it's like the 37%, and this is the 2021 data, and it changes every year with the new reports coming, but depending, like, this data is from United Nations Environmental Program and their publication. But buildings are responsible for 20% of the global emissions, like CO2 emissions, and this is well known, and this is also other known thing that the population in the cities are rising, and then they are expected to go beyond like millions and doubling in 10 years. And this is again coming from United Nations data. And the other fact about right now our lives and like the world that we're living in, that people are moving towards the urban areas. And we know the facts, like, because there are more economy the related decisions that people make, and then we like agriculture, like many reasoning behind it. But this creates a not, I don't like to call it a problem, but problem in terms of creating this like energy consumption and contributing to the climate change fact, global warming. That is the main concern that my research group team were focusing back at UT Austin. So for these like listed reasonings, right, like buildings consume lots of energy, we expect the urbanization become a major problem. And then we know that, like, you could hopefully we all know that you can use like building energy modeling tools, that the individual tools, to predict the consumption of buildings. But then the recent focus, like, kind of like changed the gear towards like urban building energy modeling. So with that, there are also platforms that are evolved, and simulation tools that has been created by strong research teams, and these are just a couple of them. But what the urban building energy modeling does is basically predicting the consumption, like energy consumption of buildings in a larger scale. And that scale, which we will get into it, like the spatial resolution, that could change from small neighborhood to a city scale, right? So it could be only 10 buildings, or it could be 10, like there are studies with 100,000 buildings. So I listed these softwares, but in my research, we mainly use Citizen software that is based in Europe. So just to give that background before we jump into the discussions. But the overall structure with the modeling is like, you have the model, but like you cannot create the model without having the data pre-processing or the data itself, right? So you need climate data, sometimes microclimate data, you need geometry data, you need like we have this archetypes like that are sometimes available, sometimes not available to us. For us to be able to correctly model the urban environment or any environment that has more than one buildings in this platforms, we need to access lots of inputs, like occupancy, for example. And many of the studies that are done to include like 10,000 buildings, 100,000 buildings, it's hard to have that data availability. It's because of privacy concern, the computational resources, cost. So you won't be easily accessing them. Plus, you won't be easily modeling them, again, because of the limitations that computers have. And that is one problem behind, or limitation behind the urban building energy modeling. And many studies you will see they have they created the models, then they validated their models, but for better modeling, or let's say for better output prediction, to get rid of uncertainties in the model, that because you don't have data for every detail. So you need model calibration. And for that, you also need to perform input sensitivity analysis. So this is like the kind of structure of the behind the urban modeling. And then for model calibration, you need measured data. Plus for model validation, you also need measured data. And this measured data could be in different resolutions, including spatial resolution, also temporal resolution. The spatial resolution, for example, measured data, you can have the data that is only available for the whole neighborhood, and it's aggregated in aggregated form. So or you could have individual building data that is very unique situation to have it in a big larger scale, and that's very detailed data. And you could have no data, then you won't be probably performing the model calibration. But again, it's the validation excludes the model calibration and input sensitivity analysis, because you have the measured data, but you have it for an aggregated neighborhood, or aggregated or in an aggregated form for a city. You know how much the city consumes annually, so you could still validate your model results by showing this is the error that I am getting. But the question we had, right, is it really enough? Or is it really proving that our model is accurately predicting the consumptions and what happens if we try to make a projection under climate change, how that differs, the error differs if we have individual level data versus aggregated level data at different resolutions, or if we have hourly data versus annual data. So again, this is just giving the background, but I did my PhD at UT Austin. So this is, it was a privilege. On the other hand, because it made my PhD easier, because UT has this, these are just a couple of examples from the buildings, but we had in the main campus, we had over 135 buildings, around 135. It might not be exact number, but that's what I put in the model initially. But we had the privilege to access the recorded measured cooling and heating consumption data for each building. So when we come up with this, I was studying urban modeling, but I was like, okay, we have access to this data, and we could test if we use different resolutions, how our errors actually are changing, right? So that goes back to the question we had initially. Yeah, people are reporting their results in an aggregated form, and I don't know, maybe it's not the best representation with the 130 buildings, and we only had 70 eventually at the end. But that was the first idea, how our error will change if we use aggregated data versus individual level data. And we created this model again for 135 buildings, but eventually ended up using only 70 buildings because of the data, the consumption, cooling consumption data for some buildings were not going back to 3 years ago. So we were using the measured data for the last 3 years, excluded the COVID time, but to be able to make that discussion. So when we started modeling, it's like you saw here, there are multiple ways that how you model your geometry in an urban building energy modeling, right? We, as a modeler, we make simplifications. Again, I had privilege to access the blueprints of this UT building. So for that, I was able to get the height information for each building. I was able to get the window to wall ratio for each building. So the level of details are described for the city modeling, and it like, as you see, the LOD 0, LOD 1, 2, 3, 4, and from the LOD 0 it goes to the 4 with the more detailed information. So like if you only have the floor area, and probably this is not even a precise floor area, right? Like it's just rough floor area, then it's LOD, a level of detail 0, because you have very limited information. And Dr. Philip, and like this like he was the co-author in this paper that I'm presenting now, but he in his PhD he refined the LODs that are only for 0, 1, 2, 3, 4, because again, in here, like the initial LOD 0, you had very rough floor area, but with the information that is now available to us, like the, like even Google Maps, like Google Earth, you could have OpenStreetMap, you could have more detailed information about floor area of many cities. Yeah, there are even like online platforms you could just pull that information and put it in a Rhino, Revit, 3D modeling tools. So anyway, Dr. Philip Biliecki, he refined these LODs, and I was like, we were planning to use them to describe our model, right? Like what kind of simplifications we made. But this is these LODs are defined for residential building, which were applicable to commercials as well. Like in terms of, here you have detailed floor plan, and then you go to LOD 3, you're detailed information about like window to wall ratio, like the roof, pitch roof, how, like what's the angle. So that's more detailed information. But in my study, or the UT study that we did, I was able to get the height information. I was able to get the floor information. I was also able to get the window to wall ratio, right? So this brought up a question, like, again, questioning that if this refined method LODs are enough to give away my outcomes, like such as, like if I list my model as LOD1 in my paper or in my any publication that I share with the academia, will that be enough to really inform them? Because yes, I could mention it's the window to wall ratio is very precise, but could we refine this LODs to make it easy for reporting? And this, like, going back to literature review, that we had, we started doing it and figure out there are model simplifications that people used LOD 0, but it wasn't really LOD 0 because they had additional information such as window to wall ratio or roof, like detailed roof with window to wall ratio. Because if you look back here, so you have flat roof for LOD 1.3. But you could also have individual ratio for flat roof. That is not defined here, right? So again, model simplifications. And if you look at the study, like we have limited real-time data on building level, which is privacy concern. And we kept reporting errors on an archetype level and aggregated level. And we also had like an inconsistency of the reported error. Sometimes it's reported as the CVR and E, and sometimes root mean like a cubic root mean error, like a different, like sometimes it's just percentile given as error. So many different sub things. Plus, it wasn't clear if they used aggregated and reported aggregated data and reported on aggregated or reported on a individual building level. So the first question, like how should we report our results? So like anyone else who is keep doing or continuing our research would see like the models and their errors, like if they need calibration or not, in which form that they need calibration or validation. So we needed to come up with a reporting way so everyone could see the like how that differs for each model, like simulation tool. And what were the spatial and temporal resolutions necessary to validate, right? So you're validating it, but how much it differs when you have the calibrated model versus validated model. So, and when we perform, so the Bayesian calibration, we'll talk about it, but it's a calibration way that many of our research teams around the world are using to calibrate urban building energy models, even also building energy models. But when we use the Bayesian calibration with aggregated data, because if we don't have building data, right? So how that improves the prediction of cooling demand, and how should we aggregate? Like, is there a way that could be more beneficial to aggregate the data for Bayesian calibration? Or, like you use annual data. What happens if you use monthly data for Bayesian calibration? So how that differs from the annual? So these sort of questions that we wanted to answer in our study. So this is, again, refined level of detail, but we called it multi-dimensional level of detail. And again, like you see that you could model, this is also valid for building energy modeling as well, like individual modeling, right? So you could model your building as the so G stands for geometry. We have the thermal zone level of details. We have the spatial resolution LODs, and we also have temporal resolution LODs. So every time someone's does the study, they could report their findings as this is done by using geometry, LOD 1.0.1, and then thermal zone assumption with a simplified thermal zone for the whole building, just one zone. And then so this is the reason. And again, here what you see is like we LOD1 is the structure without the roof, like having the roof simplified. The overall LOD1 is like flat roof, and the second LOD2 is the pitch roof. And this could be extended, like if we have more information to report, like, you have the model as just like very simplified floor plan, very simplified height, then you could report it by using GLOD 100. And if you have height information, and also floor information, but not the pitch roof, like as it is in the like in real life, if it is. So again, this gives that option to the people to have that consistent reporting. So for the thermal zoning, and this is, again, these are all coming from the literature, right? So I've gone through literature and figure out what people have used in their model. Like if they use simply like a single zone for the whole entire building, or they use single zone per floor, and then that is thermal zone LOD1. And then if they have more information in like perimeter and core, that's LOD2. And then they have perimeter and core per floor, and that's LOD 2.1. And if they have like the zones for every room, then that's LOD 3. That's like again how we like structuring it for reporting consistency. For the spatial resolution, so if the study doesn't have any calibration, then we report it as like LOD 0. So no calibration, it's just validation. And if it's calibrated by using archetype level data, then it's LOD 1. And then if it's aggregated level data for exact location, right? So the archetype, like for example, you are simulating a neighborhood in London, and then you could use the archetype level data from the London area, even maybe Europe, like in the nearby like cities, if you have the same like similar weather like better profile, right? But for aggregated level, it's basically the same location. Like you know your neighborhood, you're modeling it, and you're aggregating, or you're getting aggregated level data from the city that has specific aggregated data for that given neighborhood. So, but you could aggregate the data based on that district, like a location, exact location. You could aggregate it on a construction year. So the city of London, I don't know if London has this, but city of London, for example, could give you for that exact location data that is basically split it into construction year without giving information on the building, right? So you would know, I have 10 buildings that are constructed before 1960. I have 20 buildings in that area that are constructed in between 1960 and 1980. And then I have 30 buildings. So the London city will give you data for that 10 buildings aggregated form. So you don't really know individually which building consumes what, but you know that those buildings that are constructed before 1960 on that location are consuming annually this much, monthly this much. So that was the, again, the reasoning behind. It could be based on primary use type. Again, you have 10 buildings that are residential. So the city is giving you aggregated data for that specific location on primary, depending on primary use type. You don't know which building consumes what. And it could be also the city could use unsupervised clustering methods to again cluster that, like let's say you're modeling 10,000 buildings in London, or I have lots of people from Italy, Rome, right? So you ask the city and tell them you could cluster the buildings and give me the data for the cluster, like that clusters, and without telling me which building consumes what. And then these are, again, this could be extended, like if the data given in a different form without leaving the information on individual building and protecting the privacy, and they could be tested as well. So in our study, these are the ones that we tested, and we also had the data for building level, right? So every building that we had data, hourly data back 3 years ago, like the whole 5 years, even more, but we used only last 3 years. But with that saying, like we could also test it, how much error we get if we use spatial resolution for like LOD3 building level. So for the temporal resolution, Again, this data could be given as annual measured data, or monthly, bi-monthly data. It could be given as weekly, daily data, and it could be given as hourly data. So we put these, like, like, again, reporting consistency. So if you're using weekly data to discuss your error, how you report that. If you're using weekly data to calibrate your model, which will be very time and computational cost required, but let's say you do it, how you report it. So that was the multi-dimensional LODs we needed to define just to be able to report our findings. Also contribute to other people's findings and make it easy for someone to look back at literature review and figure out the models. So for Bayesian calibration in our model, I'll get this question, but let me clarify that from the beginning. So again, we had area, footprints, window to wall ratio for UT campus, and we only modeled 70 buildings because because of the data availability compared to 135 buildings on the campus. And we had access to data, hourly data. And here I said, like, campus meter cooling consumption data. So we had cooling data and heating. Our calibration model is only performed for cooling consumption. So we calibrated our model to predict cooling consumption because the city of Austin is dominated with the cooling loads, and the future study of this follow-up study will be climate change discussion. So that's why we wanted to discuss the cooling demands. And the Bayesian calibration is performed by using annual data, also monthly, but I'll give you brief overview of what happened with the monthly. And again, it's a kind of future study. But the discussions on the errors are done for hourly results, weekly results, monthly results, and annual results. So using annual data, how much error we got on hourly level, how much error we got on weekly level, like monthly level, and that goes on. This is like a statistical calibration method, right? Like many of, again, researchers are using it. We do describe a prior distribution to unknown parameters. And before this, we needed to select which parameters are, like, we don't know the temperature set point for the given building. And we don't, but that input is really important on our output. So you need to make that discussion on, like, which inputs you will be calibrating, because with the amount of input that you decide to calibrate, that will exponentially increase the time that you consume for computational resources. So therefore we did the sensitivity analysis before, and we come up with this 5 input. That is like temperature set point, infiltration rate, walls U value, roof U value, and windows U value. So we decided that these are the parameters that will like, if we calibrate it, our model will be predicting the consumption more accurately. And we've used, like, so again, you describe a prior distribution, and you have Gaussian. I define Gaussian normal distribution, but again, that's a future study discussion too. Like, it should be in the literature. It's very limited. There are very limited studies about it. So we might need to even discuss more distributions to be able to get different posterior distributions. So once you perform the calibration, this is our initial probability. So we say this graph is basically saying like the temperature 19 degrees Celsius, 20 degrees Celsius, 21, 22, and 23. And I am missing x-axis, but it's the Celsius degree. And it says the probability of having these temperatures, like the these temperature is like 20% per each. And that's the prior assumption, right? And I don't know which one is the final one without doing the calibration. But then when I perform the Bayesian with the Gaussian normal distribution, I get posterior distribution. So this is my posterior. It says the likelihood of this building having 23 degrees Celsius temperature set point is the highest. So for that, you go ahead and update your model to change the temperature for that given building. But this is again, so what you see your giant like figure is for each building. You are basically calibrating parameter for each building, and you know the consumption for each building. That's how you do it. Otherwise, you won't be able to do it for each building. You do it in an aggregated form. So these are the distributions that we got, the likelihood, and many of them, so this was our kind of like a finding, but it slightly changed for some buildings, and the others, it didn't even change from the 20%. So again, with the fire distribution, we might need it to have a more discrete, like a, maybe including 19 and 19.5 degree Celsius, like creating that discrete like a distribution before prior to the posterior would have been more helpful. And I'll keep like judging my study, like not, back and forth. But it's helpful for whoever's, interested in going into details, like to learn more about that and try different things. So when we performed Bayesian calibration on each building, so this result is for spatial resolution LOD3. So it's building level temporal resolution. And then we're using annual temporal resolution, like the data is available for annual. So this is just validation though. I'll show you the after calibration, what happened, how the error changed. So in ASHRAE, there's an allowed annual CVRMSE square error, the 5%. So when you validate your model, this is also another problem, but not a problem, but it's another issue that we should address, is like having this is for building energy modeling standard. So it's 5%, right? And then because we did it on the building level, I could have discussed it with the 5%, but we need new regulations on the urban building energy modeling, how that error should be in regulations. Anyway, with the validation, so you see the dark blue, which is simulated data, and then you have measured data, measured annual data. The error is, for some cases, is 100%, like and again, CVRMSE, but some cases it's 10%. So with the validation on building level. So that means some of them are in a good shape, but overall we have 41% error for the whole campus. When we do the Bayesian calibration with the annual data, right, it's the highest, lowest temporal resolution, 0, but we still get our buildings building level performance way better than the validation. So the issue with this, like, again, we don't expect everyone to have LOD3 because it's a special resolution at building level, even though we don't give away which building is what, but still it's we don't have that data on building level. So this is the validation, again, validation results. So if we were going back and validating our model and showing you the results without showing you building level on aggregated level, how would that change your error perspective, right? So in building level, we saw it's 41, average 41, and for some buildings, it's 100%. So if I was reporting as it for all buildings, the whole campus, without giving the details on how it's just aggregated on a location base, right? Then my annual error would be reported as 34, which is way below than the average of individual level, right? So you would think this I did great job on modeling, like 30% without like calibration is a not too bad on an aggregated level. But if I did the validation on an aggregated level with the construction years, then you would see some fluctuations, because before, so again, because of the assumptions that I made, right? Like I made an assumption about U value of building properties. I made an assumption for the temperature set point, the deterministic assumptions, not calibrated. So that changes how your error changes. So like for buildings between 1980 and 2004, I got the minimum error on annual level. Because we're using annual data to calibrate the model, it's normal to have higher error on an hourly level, right? If we were using hourly data to calibrate each hour, again, this like a giant, like a time and computational cost resources required, then my daily, weekly, monthly, annual, like the other errors were going to change, fluctuate a lot. So because I'm doing it on annual, my reporting on annual is a lot lesser. Same for the, so this like a CA is classroom, building, housing, office, administration, research lab. So if I was given the data and validated model on a use type, then I would get less error on housing, and this will change for other applications, but this is what we got for the UT campus, right? And the LOD 2.3 is the supervised, like unsupervised, like the classification that we did, right? So that is also giving us the error clustering. So we clustered the buildings and then gave the data to the person who simulated model and tested, and they said, okay, good, I am only getting 25% error for class 1, class 2 is 44, class 3 is 24. So and it's the highest, I mean, like again, the key finding that we have here is that we got the highest difference between hourly and annual temporal resolution is obtained for housing. And primary use types that we found plays an important role. And this is because that we had initial schedules assumptions, right? There's uncertainty in the model that the schedules of the occupancy. So that changes like how our model predicts. Yeah, and then we got daily, weekly, and monthly temporal resolutions closest to each other. So we could have like this daily and weekly is temporal resolution LOD 2. So, and again, they could be reported in one LOD. So this is after calibration, and if you were reporting this, after you calibrate, right? Those discussions were validation, no calibration. And here you calibrate your model by using all buildings data, and you improve like from 25% error that near 25 that we've seen, and less than 10% for overall buildings consumption. Same with the other classes. So all of these approaches that we found is like can be used for annual cooling consumption forecast under different scenarios. That means that with this error, like if you're given data, aggregated data on this different levels, you could make a forecast for the whole for the buildings that are built before 1980, for all buildings, or for buildings that are classroom and academic. But you can't, I'll explain why, but you cannot forecast like the impact of climate change on an individual building. So the whole forecasting should be done like however you calibrate it, like aggregated the data. Because if you, I mean, again, we were privileged to be able to look at that. And because we know that each building consumption, we went ahead and looked at 70 buildings, how much they had change in error. So this is the overall, right? Overall, all buildings is improving the error. But if you look at individually, like some buildings are performing a lot, like giving much higher error than the others. So even though overall forecasting is appropriate, like you cannot suggest a retrofitting scenario for one specific building by using aggregated data. So again, it's either improved or worsened for these 70 buildings on campus, and it improves the results on an aggregated level, but it would result in 40% error change on the building level prediction. So, and then like with the, like looking at the distribution of the errors, annual errors for each building, we figured that it would be better to use the LOD 2.2, like the median error for the LOD 2.2, which is the aggregated level on use type, like use. So the LOD 2.0 aggregated on a zip code level, 2.1 is construction year, and then use type, and then the clustering method, the LOD 2.3. But the median error for the overall annual consumption is less with the use type. Again, this is related to the scheduling and occupancy thing. And then we also looked at we did the t-test to figure out like how that changes for 70, like between each method that we use aggregated. But aggregated group of measured data used to predict the annual cooling demand is significantly different than what the annual building level error is. Again, annual building level is significantly different than the annual aggregated level. But we also concluded that based on like the aggregated level data based on construction year and based on clustering method is not significant. So it didn't really, probably it was because of the way we clustered it. It took the construction year had the more weight. So it didn't significantly change for individual building level. So what we contributed is, this is what I think, but you could correct me. So we've proven that Bayesian calibration with annual data improve the model. So we performed the monthly, again, I was going to say it, but monthly didn't give us different than the posterior distribution that we got by using annual. So it was going to, we were going to use seasonal monthly data because it's basically the temperature distribution and everything. It didn't really play an important role, and the major contributor was the thermostat set point. So and that's why like we didn't provide the solution for monthly. If we had the seasonal monthly data used to calibrate the model, then we would have gotten different seasons. So in CitiSim model, you're just to clarify that, we only have one set of temperature, 24. It's not season-wide, like you can't describe it. It's just whole year, whole building. And for that, it takes longer time. But anyway, so that's why we didn't provide the monthly data. And we provided different aggregated approach and discussed the performance of Bayesian calibration and introduced the level of the multi-level of conception. So the many of limitations as expected, but constant temperature set point over time, discrete uniform distribution, again, as I discussed, and then Gaussian normal distribution. So thank you. And questions, and I'm a little late, sorry. Yes.
Thank you, Aisha. That was really interesting and super detailed and really helpful for those of us working in the area. We've got a couple of questions in the chat already, so in the Q&A, not in the chat. So please do keep putting your questions into the Q&A. The first one that I have is about clarifying what you mean when you talk about
Aggregated data.
You could just recap that. That would
Yeah. So you again, just giving it as a neighborhood. Let's say that I have 10 buildings, and I don't want to share the individual building data, but you could sum them, average them, and then aggregate them and give that to like per square footage consumption, right? You could say in this neighborhood, I have buildings that are constructed before 1960, and the square footage like energy consumption for this is 5 kilowatt hour per meter square, to make it more sense for European attendees. So with that, you could still validate your results, right? Because you're predicting the consumption per meter square. What's the kilowatt hour consumption, energy consumption, cooling or heating? Like when I say energy, it might be a little misleading. It's not. It's cooling and heating. It doesn't have lighting, the miscellaneous. It only has the cooling in my case. So that's how you aggregate like the data. But you can aggregate it on a just location base, or you, as I said, you could aggregate it on a construction year base, on a use type base, and give me just the consumption per square meter. I'll provide my error to you for that given location. So that's how you, hopefully I was able to.
No, that's great. Thank you. And the next question really follows on, I think, almost precisely from that answer, because the next question is the CV RSME the mean of all the individual building errors, or is it a district view comparing the total?
For some graphs, yes. It's the district. So again, it's how you report it, right? You could report your mean of all individual buildings. You could report the error just for one building if you have data for one building. And you could also report your error at a district level. In my results, some graphs, and I think I put the name of my paper, but it has like more kind of better clarified explanation for the errors of each graph. But in some graphs, it was just the mean of all district. So again, if you're providing me error for all district, that could mislead me if you're proposing something on a building level. But if you're proposing something forecasting on a neighborhood level or a district level, then that's a good comparison, because I know the error of your model at district level.
Thank you. And another question about the calibration errors is about why if you could just explain again why there's less error for the model that's calibrated at an annual temporal resolution than when it's calibrated at an hourly temporal resolution.
So I did not calibrate it hourly, and the hourly results are the errors at hourly level. So as I said, limitation of the tool is that you have one set point temperature or one value for the entire year. And if I calibrate the model for hourly, that means 8,760 hours. And I need to run that much simulation just for 1 hour, like just one model. And then with the exponential, like how it gets crazy with the number of simulation, like I probably would have run million buildings just for 70 buildings. That's why again, it could be easier in an like if I create an algorithm, like I could write a code script that collects the data and runs the simulation in a faster way. And again, I had the privilege of using the supercomputing, but not everyone has that. So in Texas, we have this Texas supercomputing center. So for me, running 1 million simulation would take maybe a month, even though it's still too much, because the idea of using UBEM, urban building energy modeling, is to make predictions in a shorter period of time. If it's going to take a month, you would run, like, if 70 buildings is going to take a month, then I would suggest like running each building separately from like without putting it in UBEM, if that makes sense.
Thank you. I'm sorry, my dog has come to tell me that it's time to fed him, so we'll just ignore him just now. So the next question is really about how you see your work being used. So how do you see others using it? Do you see it being used in actually in practice, in sort of engineering applications, or do you think it's perhaps more academic applications for research?
So initially, yes, it is the academic application. That's where I come from, right? But I worked for industry, and also knowing that industry needs this, as again, I was saying, like, I wouldn't run 70 buildings if I was in industry for a month, right? No one would do that in industry because they want practical, they want something that has less error, and then they would get like, that was the reason I pointed out ASHRAE standards, which is, even though a US standard, I don't know if the Europe has standard for the error on the building level, but they need to come up with an urban level, because in building level 5% could be like a very precise, but in urban level, maybe 20% on an aggregated will be enough to make forecasting under climate change. So that is for policy making, regulations, deciding on regulations, and if there's a new and this is happening. I'm from Turkey originally, and this is like, take Turkey as an example. They're now, I don't know if they're doing it, but because of earthquake, that they need to redevelop the whole city. Like they would have just put like initial new construction in a mass form in urban modeling tool and predict how much they will consume for the heating consumption, cooling consumption, which are the dominant energy consumers, I guess. Like I mean, I hope the industry will take over at some point once we improve the overall UBEM.
Thank you. Next, a question about a recommendation. So someone looking to learn about calibrating buildings using Bayesian methods, are there any publications you would recommend?
This is our publication. I don't know if we were we will be able to share the slides. I can, but how spatio-temporal resolution impacts urban energy calibration. I have the details about I don't have the data shared, like the model, because of the privacy. But there's also another study from Clayton Miller's group from University of Singapore, and they have the Bayesian calibration in the same form that they share the, and it's a different, but you need to do some adjustment, but it's very useful source if they want to go ahead and find that. I can't find it and send it to you.
Yeah, that would be great. What we can do when we post the video recording of the webinar on YouTube, we can put in some links for some of these resources. There was another question about UBEMs more generally, which I've suggested a resource for in the Q&A as well. So now the next question I have a query about. So if this is your question and I've got it wrong, please let me know. But the question, I think, is asking what you think about incorporating now IA. Is that indoor air quality?
It's artificial intelligence, I guess.
AI.
AI.
Yeah.
I guess so. No, I'm not sure, but.
So, Aisha, do you want to share your thoughts on that?
Yeah, sure. We did actually, we incorporated AI and predicting replacing UBEM. So, it's a very common way right now, like with faster solution. We had the CDDNN project. Again, it's under Zoltan Nagy's, Dr. Zoltan Nagy group intelligent environment laboratory. So we discussed like how we could create the surrogate model and replace the citizen to predict faster. And for the calibration, first we need to go ahead and test our model, like if like with the validation, right? Like we need to validate our AI or deep neural network for the accuracy. And then we should hopefully go ahead and make it faster for calibration. It's a great idea. I just don't know how right now, but it would be like a great way of replacing this too much time-taking, time-consuming way with AI.
It is the big problem of urban building energy modeling at the moment, for sure. I'm really impressed with these incredibly thoughtful questions that people have for Aisha. So the next question is about your results around the calibration with monthly energy data, noting that the calibration with monthly energy data didn't improve the accuracy of the model.
Yeah.
I'm wondering if that is possibly because some of the unknown building parameters weren't granular enough, which I think it's partly something you touched on in the limitations yourself. Do you want to say more about that?
And then it says, were they two cores? Not only, I mean, the same thing, same idea, but yes. So the granularity in the, like here, you could see it's only 5 discrete, like probability. It wasn't enough to give me posterior distribution. Even maybe like the minimum and maximum wasn't enough. So that needs, again, with the 5, again, I don't remember the exact how many simulations that I did for the calibration, but I know it was a lot for 5 input. And the other thing that I was thinking, instead of calibrating 5 inputs, I would have increased the granularity of the temperature set point, which had the major contribution, and maybe infiltration, and then keep the rest out to see how that will, like only having 2 input calibrated with higher granularity versus having 5 input with less. So that's one study suggestion if someone takes over and want to do it. So yeah.
There are a lot of questions still to be answered out there, that's for sure. And then a final question, which is noting that it's a bit counterintuitive that the calibration gives more error in the more detailed case, so in LOD 2.2 rather than LOD 2.3. And based on your research, would you suggest that maybe a level of detail LOD 2.2 is enough to model a neighborhood?
I'm assuming this is for spatial resolution, not for geometry or anything. So I understand that why, like so more detail gives more error because the assumptions plays more important role on the when you detailed it. So as like LOD 2.2 is the user type, and yes, in overall user type, because the schedule, right? Like it's the cooling consumption. So, and I'm defining a schedule for occupancy, and that occupancy will change the heat gain and losses in the building because they create, and because it's a university building, we have 1,000 people. So that schedule will really change the heat source inside of the building. And that's why that's my, again, assumption that's why it played more, like gave me more error on an individual level on a building. And I can't say which one is enough to model because this was only for 70 buildings. Yes, it gives so LOD 2.2 is enough if again you're making suggestion forecasting on a classroom buildings. But if your goal is to, and mainly our goals are to retrofit buildings which are built before some timeline, right? So then it would be better to aggregate it based on the construction year and make the suggestion forecasting on on those given construction year built buildings, if that makes sense.
Thank you. I think that's a great note to end on. And thank you very much to Zoltan for sharing the link to the City DNN paper, which we'll add to YouTube as well. Thank you, Aisha, for that. That's been really really brilliant, and I think I mean I've certainly found that incredibly useful and interesting. I'm just going to swap back to my slides, and I will hopefully you can see my screen now, and I'm just going to finish off. So I have just to remind you that we have one more in this series of seminars coming up, and that is in November. That's going to be Tianxing Hong, who's going to be talking about the challenges and the opportunities that there are for urban building energy models to round up this sort of theoretical strand of the UBEM webinars. But this is not the last that you will hear about UBEMs from the IBIPS Education Committee. One of the topics that people had asked us to do more about was thinking about what the tools themselves and how they use them. So I should have details of dates quite soon, but we're hoping to have a series that will give you a bit more of an introduction to how you actually use some of these UBEM tools in practice for actually carrying out investigations. We also have our ongoing simulation best practice series, which is not specifically focused at the urban scale. And we will be bringing you in the new year another series which is on occupant-centric simulation-aided building design. So do keep your eyes peeled for details of all of those, which will be announced very shortly. So those details will go out to the IBIPS mailing list. If you're not on the mailing list, you can join the mailing list. I'll put the link into the chat there. And we also share the details in the IBIPS LinkedIn group. So do join that as well if you would like to see that. And do let us know. You can let us know on LinkedIn in particular, but you can let us know here as well what topics you'd like us to cover in future seminars. So are there topics that you think you haven't heard enough about? Are there things that we've talked about but you'd like some more detail on? Do let us know what else you would like to see us cover. Now you can vote now, and you can keep voting after the end of this as well. So do please let us know. The recording for this session will be on the YouTube channel, which is called IBIPS University. Do subscribe to that. You've got all of the recordings for all the seminars that we've had over the years that the committee has been running these. So I think hopefully we will get the recording for this session uploaded at some point tomorrow. And if you subscribe, you'll be able to get updates whenever the new versions are uploaded. So finally, all that remains for me to do is to thank Aisha again, and to end with a plug, which is now my new routine, which is to invite you to join IBIPSA as a supporting member. So obviously, you can join these events and participate in all of this without spending a penny. That is entirely up to you. However, if you are able to join as a supporting member, then there are some benefits to you. The first thing is the access to the journal, either online or a print subscription as well, the ability to use the IBIPSA supporting member logo, and of course it is an incredibly reasonable price, which hasn't changed in the last 2 or 3 years. These are still the pre-pandemic prices. So I will leave you with that. You can see the details on the website, so do consider joining up there. Thank you again, Aisha. That was absolutely excellent. I enjoyed that tremendously and learned a lot, and I hope everybody else did too.
Likewise, thank you.
Thanks. Bye.